All right, so in this video, we're going to graph rational functions. If you remember, rational numbers are numbers that can be written as a over b, where b is not equal to 0. The shorthand way of saying that is anything that can be written as a fraction. And so we are going to graph functions that have fractions in them, and not just fractions, but where your denominator has the variable, your numerator has the variable. You got to pay attention to a lot of different pieces. A lot of moving parts here. So there's a bunch of steps that we're going to follow. They're pretty easy once you get them down, but make sure that you do follow the steps. Okay, so our first step, and I'm going to go into problem number 1. If you guys have your note sheet, all of these steps are what we're going to be doing. Okay, so if I look down here at problem number 1, first thing I want to do is factor it if possible. And I'm going to take a quick look at that numerator, 2x plus 3, and I can't factor that. And I'm going to take a look at the new denominator, x minus 1, and I can't factor that. So we're done, all right, as far as the factoring and canceling part goes. But I do want to find a y-intercept. All right, so I'm going to make a little note to myself over here, and let's say I'm going to find my y-intercept. To find the y-intercept, I am going to set x equal to 0, all right? So y is equal to 2 times 0 plus 3 all over 0 minus 2, which turns into 3 over negative 2. Okay? So my y-intercept is then the point 0 comma negative 3 halves. Okay? So we found the y-intercept. Yay! But we're not done, of course, because that was only step 2. Step 3, we want to find any possible x-intercepts. And so to find the x-intercepts, we are going to set y equal to 0. Remember, y can also be represented by f of x with these functions, so you would also possibly set f of x equal to 0. If we set y equal to 0, we are going to say 0 is equal to 2x plus 3 over x minus 2. Now, I want you to put your fraction thinking hat on, all right? And I want you to really think about fractions and the possibility of how can a fraction be equal to 0. The only way, and I really do mean this, the only way a fraction can be equal to 0 is if the numerator is 0, all right? 0 divided by any number is 0. So this any number at the bottom doesn't matter to us, and eventually we'll talk about what happens if the denominator is equal to 0. But if you want to make a note to yourself to find the x-intercepts, what you're really, what you're really doing is setting the numerator equal to 0, okay? So we're going to solve this. Let's see what we get here. So 2x is equal to negative 3 divided by 2. So we get x equals to negative 3 over 2. Just a note, I am sure you know this, but I'm going to say it explicitly. Your x and y intercepts do not have to match for these problems. Just be aware of that. So yes, I know this is negative 3 over 2. Yes, I know this is negative 3 over 2. That doesn't always happen. Just FYI. Okay? All right. We're going to find something called a vertical asymptote. We abbreviate it as VA. All right? So vertical asymptote. And to find the vertical asymptote, you are going to make the denominator equal to 0. Seems a little weird, but it's almost like looking for those critical values that we had looked for in the last unit. If I set this denominator equal to 0, I am looking for the very specific number that has to be thrown out of the domain. All right? If x is equal to 2 in this problem, right, 2 minus 2 is 0. And so I have some value in the top. If that's 2, what would that be? 7 over 0. And 7 over 0 is undefined mathematically. So you can't graph something that's undefined. So that's where we talk about having these vertical asymptotes. It's what happens, what are those values that we have to throw out of the domain. And so in this case, we have the vertical line, x is equal to 2. Okay? All right. So horizontal asymptote. What you want to look for the HA, the horizontal asymptote, is what happens in the extreme. Okay? Now, when I say extreme, I'm not talking about 100 is extreme. I'm not talking about negative 300 is extreme. I'm talking about a trillion. That's extreme, okay? And so what happens is we want to look at 2 times a trillion, 2 trillion. Now, if I take 2 trillion and I add 3 to it, that 3 really doesn't matter. It's not going to change things drastically. And if I take a trillion and I subtract 2 from it, it's a little bit smaller, but not much. So what ends up happening to find your horizontal asymptote is as long as these x's are the same degree, so first degree on top, first degree on the bottom, all you want to do is divide your leading coefficients. So in the numerator, we've got a coefficient of 2. In the denominator, we'd have a coefficient of 1. And so 2 divided by 1 gives us a horizontal asymptote of y is equal to 2. All right, so divide the leading coefficients. All right. So, but again, that's only if the powers, the degree of the terms match. So we have x in the numerator, x in the denominator. We'll talk about what happens if they don't match. All right. So y is equal to 2 is our horizontal asymptote. So what's happening with a horizontal asymptote is that's what you approach in the extremes. So when we get to, the end behavior of this graph, your graph is going to be approaching 2. For our holes in the graph, those are also called discontinuities. I had to get the right term there. The only way you're going to have a discontinuity or a hole in your graph is if you have canceled out a factor. So remember, our very first step here was to factor and possibly cancel. Since we didn't factor or cancel, there are no holes in this graph. All right, so the answer here is none. And we will talk about, there is a 7th set or a 7th step where we might have to find what's called an extra point. But in order to do that, we need to actually graph what we've got so far. All right, so I'm going to zoom in on the graph this time and start graphing this thing. All right, so I've got a y-intercept of 0, -3/2, so that's -1.5. I have an x-intercept of -3/2, so -1.50. I have a vertical asymptote of 2, x equals 2. So to draw the vertical asymptote and the horizontal asymptotes in, you want to use dotted lines because they're not actually part of your curve. It's what your curve approaches. So vertical asymptote, I'm going to come over here and give myself a vertical asymptote at x is equal to 2. And a horizontal asymptote, y is equal to 2. Get that in there. Okay. So what happens with these vertical and horizontal asymptotes is you're going to approach them. So I know my curve has to go through these 2 points, and it's going to approach y equals 2 here. It's going to approach x equals 2 here, but it will never, ever, 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 really ever, you're never going to cross the vertical asymptotes. In very weird situations, you might cross a horizontal, okay? But that doesn't often happen. So I'm going to draw this curve in, and here's half of my curve. And the reason I say it's half is because I'm also going to have a curve somewhere over here on the right. The thing is, I'm not exactly sure where. All right. It is possible that the curve could be up in this top upper right quadrant. It's also possible it could be in this lower right quadrant. I need to test. So what I'm going to do is pick a test point that is to the right of this vertical asymptote. So the vertical asymptote is 2. Obviously, we don't pick that because we know 2 doesn't work. But I want to pick something to the right of that. It doesn't matter what. Just pick some value. I'm going to go ahead and pick 4 for giggles, all right? And what I'm going to mark this as is the extra point, all right? Apparently, I'm trying to make extra point one word. Apparently, I need an R there. Extra point. Okay, there we go. I promise I can write this. Let's make x equal to 4. Again, you can pick any value as long as it's on the curve itself, right? On this graph, it goes up to positive 10, and it's to the right of our vertical asymptote. We know what happens to the left. We're trying to figure out what's going on the right. All right, let me take a look back at this thing here. So y is equal to, now I'm going to use that x value and figure out what's going on. So I've got 2 times 4 plus 3 over 4 minus 2. So 11 over 2. Am I doing my math here right? So 11 over 2. Yeah, that sounds right. So we have this extra point, and I'm actually going to move it off to the side here. So this is 4. That was our x value that we picked. And 11 over 2, what is that, 5.5? That sounds right. So when I graph this point now, all right, back to my grid here, I'm going to go to 4. Right, here's 4. And I'm going to move up to 5.5. All right, so I know my graph goes through here. So what that extra point tells me is that this curve is going to approach this x-axis vertically, and it's going to approach this y-axis horizontally. So I now know that this curve is going to look something like that. So the green part that I graphed is the actual curve of the rational function. Those 2 blue dotted lines are not the function. Those are just what the function approaches. Okay? So the actual curve itself is the green part. And we're done with this particular problem. All right? In the extreme now, as we go further to the left, this is just going to keep getting closer and closer to 2. As we go further and further to the right, it's going to keep getting closer and closer to 2. That's what horizontal asymptote tells us. All right? So I'm going to go ahead and move on to problem number 2 here, and we're going to go through the exact same steps. We just want to see what's going on with this one in case anything else happens. Okay, so step 1, we want to see if we can factor and cancel anything. So x squared minus 1 factors into x minus 1 and x plus 1. Denominator x squared plus 3x plus 2 would be x plus 2x plus 1. So in this case, we do cancel, right? We cancel out this x plus 1 with that x plus 1. So when we're looking to find our x and y-intercepts, our vertical asymptote, even our horizontal asymptotes, you just need to look at the new function, all right? And we'll talk about what's up with that other piece later on in terms of the part that we canceled out, okay? All right, y-intercept. Y-intercept, I'm going to set x equal to 0, okay, in this new function. So don't go back to the original. Keep it in the new function. It makes it easier. It makes the number smaller. So y is equal to 0 minus 1 over 0 plus 2. So negative 1/2. Y-intercept is 0, negative 1/2. Okay. So let's talk X-intercept, all right, which means we're going to make y equal to 0. But remember, this is that kind of goofy one where really all you need to do is set the numerator equal to 0, okay? So when we solve this, we're going to get x is equal to 1, which then gives us an x-intercept of 1, 0. See, I told you the x and y-intercepts don't have to match. All right, let's talk vertical asymptote. That's VA. A vertical asymptote, you're going to set the denominator equal to 0. So x plus 2 equals 0, which means x is equal to negative 2. That's the value that we have to throw out of the domain. All right? It would make the denominator equal to 0. It makes the function undefined. It's just all kinds of problems happen there. So vertical asymptote here is x is equal to negative 2. Okay? Horizontal asymptote, I want to see if I can compare the leading x terms. So right now I have x here and an x here, so they match in degree. So now what we're going to talk about is if I have a trillion divided by a trillion, what I really have is y is equal to 1. All right. So horizontally, this is going to approach 1 in our extremes. Okay. There's something else going on with this problem, though. And the something else for this one is the whole. Okay, we actually do have a discontinuity in this problem. The reason we have a discontinuity is because we canceled out a factor. So you have to do this in two parts. First part, you are going to take the piece that you canceled and set it equal to 0. So that gives us an x value of -1. So that gives us half of the location of where this discontinuity is. The other half of the discontinuity is going to come when we take this x value and substitute it into this abbreviated function, this modified function, I guess is the term for it. So y is equal to -1 minus 1 over -1 plus 2. So let's see, -1 minus 1 is -2. -1 plus 2 is 1. So this gives us a y value of just -2. So now I know that in my graph I have a hole, a discontinuity, a break. There's lots of different ways to refer to it at the point -1, -2. So I'm going to take my two x-intercepts, or my two intercepts, my two asymptotes, and this hole, and I'm going to graph it to see if we can figure out what's on earth is going on here. So sliding over to the graph. All right. So we have a y-intercept at 0, -0.5. X-intercept is 1, 0. I have a vertical asymptote. I'm going to actually put this in highlighter so you guys can really see it at -2. Okay. And you can do the same on your note sheets, your homework sheets, whatever. Horizontal asymptote at y equals 1. The only thing I'm going to do here is make this just a touch thinner. Okay, so we're going to go to +1 here. Ooh, much better. Okay. And the last piece I want to fill in is this discontinuity, this hole. And it's going to look a little strange, but literally you need to draw an open circle on the graph. So at -1, -2, I am going to draw a hole, an open circle in the graph. Okay? So when I go to actually draw the curve in, remember the blue lines, those blue dotted lines are not the curve, it's the asymptotes that your curve approaches. Okay? So I'm going to curve up toward, whoa, hold on a second. Let me actually try and get a curve going. I'm going to draw a curve up towards this asymptote. Okay, and I'm going to draw a curve down towards this asymptote. You'll notice the hole I did not draw through, okay? It's a hole for a reason. Consider it like an open circle. You can get right up close to it, but not actually go through it. Now, we've got a problem. The problem is I know that I have a curve here on the right side. I don't know what's going on the left. There's something over here. It could be in this lower left. It could be in the upper left. I've got to find it. So what I'm going to do is pick a value that is somewhere to the left of my vertical asymptote. You can pick anything to the left of the vertical asymptote, but you want to pick something over here. I'm going to go ahead and pick -5. No particular reason other than it sounds like a good number to use. So I'm going to label this the extra point. Okay. So the extra point, I'm going to use x equals -5. Now, when I find this, I'm going to use the modified function here. So y is equal to -5 minus 1 over -5 plus 2. So that's -6 over -3, which is what, 2? So now I know I have an extra point at -5, 2. Okay, so when I go to graph this, I'm going to come over here to my curve, right? My graph here, -5, +2. And I know that this curve is now going to be this upper left quadrant, all right? So it's going to curve up towards the vertical asymptote. It's going to curve down towards the horizontal. And again, it approaches, but will not cross these, okay? All right, so I am going to go ahead and cut this video right now. There are 2 more problems that I'll put into a separate video. Hopefully that one will be a little bit shorter since I'm not going to be explaining all the steps every single time. All right, please let me know if you have any questions or concerns on this or if things aren't making any sense.